Good morning, everyone, and welcome to our series of webinars on the measurement system analysis. Today we have topic number 7 in the series of breakfasts with MSA. Today's topic is called the Apocalypse in Metrology, and it is about the uncertainties of type B in measurement process. And this is the list of topics that we want to cover in this part of the webinars. And we already know that there will be another quite an extent list of topics after this, based on the questions and based on the feedback which we are getting. Very well, so straight down to the topic itself. Let me share my screen. All right, so we are now in the part of the measurement process. We already have left the part of the measurement system, and we are talking now about uncertainties type B. Just a little reminder, the type A and type B is not at all tied up with the uncertainty itself. It only describes how we get to know that uncertainty. And certainly the choice that we should be making is getting it from an experiment. This is what we covered the last time. And now we'll cover the part if we have some prior knowledge, which is we can get the uncertainty from anything else but the experiment. And clearly, the rule number 1 is to be conservative, because when estimating the uncertainty of the measuring device, you can legally be always stating a worse uncertainty, a bigger uncertainty than is the actual status of the measuring device, but never smaller. So whenever we are not really sure what to put in, we need to put in a slightly bigger number than the reality. All right, so there can be a very long list of all the uncertainties you can think of, but certainly we should be focused on the 6 that are quite standard, that mostly appear in many of the measuring devices. And even though they are not relevant for the case we have, we should note that. We should say that this uncertainty is 0 and we know it. All right, so what are these? The first one is the equipment variation on the measured object. This is usually the one which is being done on throughout the experiment, and there is approximately I will be trying to explain what this uncertainty means. It is the width of some region in which the repeated measurement would stay. And it is an abstract concept. We know that there is not one of these regions, there is a region per every part we measure. So if there are 2 parts of different dimensions, they would create a different region. But generally speaking, this uncertainty is what would be the width of that region if we take repeated measurements. The next one, very popular, is the appraiser variation. And that is how the measuring device will perform when we use different people. And again, it is the bit of the region the measurements would scatter about if there are different people using the measuring device. The third one is the gauge variation. The gauge variation appears when we are using a set of measurement devices to build the measuring process. And in the series production, this is quite often in places where the capacity of the measuring devices is not enough to cover the full production. And there are two or more of those, and the parts go randomly or in a given order, it really doesn't matter, into more than one of the measuring devices. Then the difference between these devices is the gauge variation uncertainty in the measurement process. The fourth one is an uncertainty of a measured object. And it can be thought of in the sense that if we are measuring a diameter of a circular hole, then the circle in the reality really does not appear there at all. So the measurement object uncertainty is the difference between the ideal shape, which is dimensioned, and the real shape, which is there. So approximately, we can be thinking about this dimension. This is being simplified to tolerances of the shape or form of the dimension that we are measuring. So for example, if it is a diameter, this uncertainty from an object would be the circularity or cylindricity. If it is the distance between two planes, this uncertainty would be the parallelity of these or flatness. We would always go one step beyond the dimension which we are actually measuring. So that is an object. The fifth one here is the stability. And this is how the measuring device would change if we would be measuring the same object with the same operator over some longer period of time. So we already have an equipment variation here. But the equipment variation, it is thought of mostly that it only takes an hour, half an hour, or some short time span like that. But if we move to a whole shift or a week or a month, that's usually under the concept of stability. How the measuring device changes from spring to summer and from summer to autumn, and so on. This is one of the most difficult uncertainties to get. There are specific experiments for that. But since we are not dealing with experiments in type B uncertainty, there are other sources we can get this information from. So if we don't have a prior knowledge, we are stuck with an expert opinion. And we can possibly get the prior knowledge from the previous calibration report of the measuring device. So if the device already has some history, and there is some history of calibration, then the difference between the individual calibrations is what is meant to be the stability. In an industrial environment, this is quite often a 1 year. The calibration period for the shop floor measuring devices is around 1 year. So if you have the reference on how much it was the last year and the year before, this is how much the calibration has actually had to change the measuring device so that it is good again. That would be the stability you are looking for. And the last one mentioned here is the temperature. What would be the difference in the dimension measured if we change the temperature? The temperature is perhaps the one which we can estimate analytically. And that's because we very often know what is the thermal expansion of the part which is being measured. And this is a separate topic. We will be covering this in one of the future webinars, specifically how to treat the heat expansion and what is the measurement error on the temperature difference. But I will give you a little hint here. It all depends on which temperature changes. And there are three. The first one, of course, is the measured object. And the second one is the measuring device. And the third one is the reference the measuring device is needs when it is doing comparative measurements. So based on the state of these three temperatures and based on their change over time, possibly during the measurement time, it is possible to estimate what would be the uncertainty from the temperature. And the most basic case is if we have a measuring object and we are measuring some of its dimension, let's call it L, and we know what is the temperature expansion constant alpha of this material, then we need to multiply it by this length, and we need to multiply it by the biggest difference from nominal temperature that we will get. The nominal temperature is usually 20 degrees of Celsius. In some labs, it may be different. And if you know that your air conditioning is capable of keeping this between, let's say, 18 and 23, then the biggest difference is 3. The biggest difference from the 20 we had in the beginning. We are calculating in a thermodynamic temperature here in kelvins usually, and this will give you I'll call it UT underlined. This will give you a hint on the uncertainty that you can get. If you want to be conservative in this case, then you always have the option to estimate the difference in more conservative way, like how much it can go wrong. So this more or less covered on what the individual uncertainties are. Quite usually in the lectures on measurement uncertainty type B, this is being named, and then the user is left with filling it out. And the question arises, like, what should I put in? The user tends to be lost in that. And by did it take only that short time just to name out the uncertainties? It doesn't give much of a hint. Well, this is the reason that once you'll get used to filling this out, you will find that it is not complicated at all. You just need to either go into the experiments that have already been taken, and if you don't want to do more experiments, you just take the value which was there before, or you just get your mind spinning, you just brainstorm of what possibly this can be, the uncertainty can be, and put a bigger number there. So if you are doing this on what's called, based on what's called the expert opinion, then try to think about this like, what would be the smallest value that is bigger than the device will ever do. And with that, just keep in mind that this cannot be done correctly. We are not playing with the precision there. And if you know there is not a perfect number to put in, it is kind of relieving. You can always put a bigger number there and it will be all right. Okay, so if you have these estimates, then the next question is how to formalize it, how to fill it in. We always, when calculating the uncertainty, we always need to use the standard uncertainty. So that is something you know about the measuring device, and that something can be the equipment variation on an object. It can be the span of the individual measurements. Or you have the difference from the temperature or anything else. Then always before putting it in, we need to recalculate that to standard uncertainty. And always with the measurement error, the assumption is that the measurement error in nominal state is 0, and it can move from that 0 to some dimension with certain statistical distribution, with certain probability distribution to be precise. So on top of what we have, the something, the number something, we need to assume that there is some shape of the distribution. And in absolutely most of the cases, it is 2. First of all, if you are gaining it from some prior knowledge from experiments, this can be a standard deviation already. So the standard uncertainty then equals the standard deviation. And it is this first case that we already assume there is a normal distribution and we already have its standard deviation. So this constant k equals to 1. So that is the first case. And then there are the standards like VDA5 or basically all standards for the industrial serial production measuring devices. This one is being used. The rectangular distribution, when we are assuming that there is some limit on the value, and any value from 0 to that limit to either side has the same likelihood of happening. And in that case, the k constant is the square root of 3. Then, of course, you can have some other possibilities, which are basically around this concept. Either you don't believe it is really in the center, it is around the 0, and it is more towards the limit that you have estimated. So you want to be more conservative. Then you would go for this one, the U distribution. Or you believe the ends that you have estimated are not very likely, and it will really be smaller. And you can go for this one. Well, if you don't know, go for the rectangular. If you want to add another information in the way I've just mentioned, you can go for the U distribution or the triangular one. All right, to make it easier, Martin will now show you how this is done in Yarvin, where you can actually pick the distribution by a shape. You don't need to think about the k constant. Martin, please go ahead.
Good morning. About the uncertainties that can be calculated or that can be filled in Yarvin software, the first choice is if you want to make an experiment or not. Because as Jaroslav told you, our approach is to calculate everything that can be calculated from the data as a type A uncertainty. So these uncertainties that can be calculated is not possible to fill in as B type. So first, to show you what all the uncertainty budgets we have, I select no experiment, and we have every single uncertainty that can be filled in. It's repeatability on the workspace, is the reproducibility of the operator, of the measurement system, of the object, of the temperature, of the stability, or something else that doesn't fill in any of these uncertainties. And if you want to fill the B-type uncertainty, you need to add two numbers. First is the value, and the second is the coverage factor. For example, if the value will be something like this, and the second is the coverage factor, and here depends what the value represents. If the value represents uncertainty, you will choose the factors of 1 or 2. The coverage factor equals to 1, it means that this number represents the standard uncertainty. If the number is uncertainty that is expanded by the factor of 2, you will choose the second one. If, for example, if this uncertainty came from some kind of calibration protocol. If you have, for example, some special case when the coverage factor is 3, it's not here in the standard selection. You can add it as the custom value, and it will be stored here for your purposes. In the lots of cases, the uncertainty is the same for all the characteristics. So if you want not to fill it manually every single for every characteristic, you can just use for all, and then the numbers you filled in are copied for the every characteristic you have. So this is the basic information how to fill the uncertainties. You need two numbers. You need the value. It can represent the uncertainty, or in second case, it can represent the error from the source that this uncertainty represents. And in this case, you have three distributions: U distribution, equal distribution, or triangular distribution. And as before, the coverage factors are then calculated from these distributions. In the second option we have is when you have an experiment. The first you have to do is to choose something that is the greatest influence factor. And it means that this greatest factor, I go, for example, for the gauge variability, will be calculated as type A uncertainty. So if you go to the B type, you can see that we have some uncertainties disappeared, and the ones that are missing is the greatest influence factor that we choose in the previous step. That means the uncertainty from the gauge variability. And the second that is missing is reproducibility on the workpiece, because those two uncertainties will be calculated from the data. It will be calculated from the experiment that we define in this step. So this is the way how you can add B-type uncertainties into Yarvin. It's nothing difficult. You just need to know what is the value, what the value represents, and according to this, you will choose the coverage factor. That's all. Now we can go back to Jaroslav.
Thank you very much. All right, so there is one more note which I wanted to make, and that is on how conservative we should be. And I have said more or less, do anything but be conservative. So what is the impact to the overall evaluation? There may be a fear that if the estimate is too conservative, the measuring device would not be acceptable. And yes, that's true. But the result, it may surprise you that it is not really that much of an effect to the result as one may estimate. Oh, I'm sorry, I have here a few things in check. So here you have the formulas on how the uncertainty of the measuring system and then the measuring process is being calculated. And it is always a square root of a sum of squares of the individual uncertainties. There is one exception. On the equipment variation, which is taking a maximum value from a few of the uncertainties before. But other than that, it is always a sum of squares and then a square root. Even with this maximum, there is one uncertainty which is a square. So this rule is not violated. And it is the same as the Pythagorean theorem on a triangle, as it is down here. So when you are combining these uncertainties, and let's say that you will sort them from the biggest to the smallest, then the biggest one would be down here. Choose red color again. the biggest one is down here, and then you take the next one in the right angle and you sum them up geometrically, and then the other, then the other, then the other. And you can see if you add 3 more to the first one, all these 3 added to the first one, it will only expand the first one by this much. So this rule of summing up the squares will not, even if all of these would be double the size they are, the U2, U3, U4, you will not end up in a significantly bigger over value, the combined value. Maybe a little bit, but certainly not excessively. So yes, you can overdo it. You can estimate an uncertainty which is bigger, and possibly this may influence the overall evaluation of the measuring device. But keep in mind that there is the way this is being calculated is putting some cover on all of that. The way this is being calculated itself assures that it is not too much over the biggest contribution that you have. If you have 2 contributions of the same size, then their combination is not twice their size, it is the square root of 2 of their size, which is 1.4 or something. It is less than 1.5. All right, so this is the final note I wanted to make. We are about 2 minutes late, and I have looked over the chat and Q&A. Haven't seen a question so far. If there are any questions, please let us know. You can write us to an email, which was part of the invite, and we'll cover your question in the future, in the next webinar. The next webinar will be about evaluation principles. So we will be jumping from the uncertainty of certain physical quantity down to the principles of evaluation of the measuring device, no matter what the measuring quantity is. With that, thank you very much, and until the next time.
Diribet, we are Diribet. Diribet, we are Diribet. Diribet, we are Diribet. We are Diribet.